Hello everybody. Today I'm going to show you how to draw the Lewis and the VESPR diagram for this funky looking ion called tellurium pentafluoride ion. So let's get started. So in order to even think about drawing the VESPR diagram, we need to start off from the basics. So we need to draw the Lewis diagram first. In order to draw the Lewis diagrams, we need to find out how many valence electrons this molecule even has. So it has 6 from tellurium, and then 5 times 7, so 35 from fluorine, and also 1 more electron that it gained. So in total, we have 42 electrons. Whoa, that's a lot. So let's draw this dot structure. Keep in mind, we need to fill this with 42 electrons. So tellurium would be our central electron. It would be our central atom. And go ahead and draw 5 bonding lines. And then make sure you don't think this is a double bond. So it's just like that. And then you start drawing your fluorines and fill it up. And making sure each fluorine has 8 electrons. And then we realize that tellurium also has an extra lone pair. And that's okay because now it looks like it broke the octet rule, but that's totally fine because tellurium is special like that. And to your right, I also have a diagram of this ion in case you didn't like my hand drawing. And you can see that this orange looking central atom is tellurium, and then the little sky blues are the fluorines. The problem with this picture is it doesn't show the lone pairs. So in this case, the lone pairs would be somewhere down here. Now this is how our Lewis structure would look like. If we drew out our VESPR molecule and we had a 3D molecule per se, this is how the shape would look like. The green would be the fluorine, and then the yellow thing represents tellurium, and the one without an atom would be the lone pair. If we look at the second diagram here, I think it's a little easier to see what happened. So these 4 right here, we call them the equatorial axis. And if you can imagine this angle right here, this would be less than 90 degrees. As you can see in the bottom, it's actually 83.32 degrees. We don't have to know all that. That's just a bunch of numbers. And this angle happens because of this lone pair right here. What the lone pair does is it just pushes everything closer. So imagine it's just pushing it closer. Oh, the diagram's getting way too complicated. So it's just pushing it closer, making this angle right here no longer 90. It's going to be less than 90 because they're getting pushed together. And same goes for these right here. These will no longer be 90, and they're going to get smushed and closer together. And the only reason it happens is because of this lone pair. Lone pair have greater repulsion than a lone pair bonding pair, and it's greater than a bonding pair bonding pair. This shape would be called a square pyramidal. And it's called a square pyramidal for this very reason. I will show you. So if we draw our square pyramidal shape for tellurium pentafluoride ion, it looks a bit like this. What I did was first start off with a square, and in the center I put my central atom, and in the 4 corners I put the 4 fluorine, and then I don't know why I put iron right there. This should not be an iron. It it should be fluorine. Ignore that. Pretend that didn't happen. So then you'd have fluorine on the top. And if you can imagine like an Egyptian pyramid, that is exactly how it looks like. So the square base is where the fluorines are, and then the pointy part at the top would be your fluorine. Again, these angles right here, the one between this one and this one would be less than 90 degrees. And so will this one and this one be less than 90 degrees. And that is how you draw the VESPR diagram of tellurium pentafluoride ion. Thank you for watching.